Today we'll be working on the following problem. Let X, M, and mu be a measure space such that the measure of the entire space is finite, and F is a non-negative real function on X, and F is be measurable. For all n greater than or equal to 1, we let a sequence E sub n to be the set of X for which f of x is greater than or equal to n. Prove that f is integrable if and only if the sum of the measure of E sub n converges. Pause the video if you want to work on this problem by yourself. Okay, let's see how we prove this. So first, just for convenience, let's define E sub 0 is the set of X for which f of X is greater than or equal to 0. Actually, this is the entire space, right? So in order to prove this equivalence, what we have to do is we want to establish some inequalities between the integral of f over x and the sum of the infinite series. Okay, so if you consider this, if you define E sub n minus E sub n plus 1, actually this is from the definition, this is the x for which f of x is greater than or equal to n, but less than n plus 1, right? So now, over this set, if we integral f over this set, what do we have? We have, if we integral en minus en plus 1, and f the mu integral over here, because over this set f is less than n plus 1, so if you integral this, it will be less than n plus 1, less or equal than n plus 1, and the measure of this set, right? And then greater than or equal to n times mu of en minus en plus 1, right? So now, and this, because it's easy to see, E sub 0 is containing E sub 1, E sub 2. So this is a decreasing sequence. And then each E over En minus En plus 1 and En plus 1 minus En plus 2, they are all disjoint, right? So now if we, so this actually becomes mu, the measure minus this En plus 1, right? So this equals to this. So now we want to find the partial sum. If we sum this n in n, right? And then you need this also, we define E sub 0. So if we sum them up from n equal to 0 to m, so n times mu En minus mu En plus 1, this less than or equal to n from 0 to m, this integral, right? En plus 1 f d mu, and less or equal than n from 0 to m, n plus 1, the sum mu En minus En plus 1. Okay, so if you expand this part, it's easy to verify because n equal to 0 is 0, and then 1 is the measure of E1 minus mu E2, and then the next term is mu 2 times mu of E2 minus 2 times mu E3, and then plus the last term is m mu of EM minus m mu of EM plus 1, right? And then for this part, you can see here when n equal to 0 is mu of E0 minus mu of E1, and then plus the second term n equal to 1, it become 2 times mu of E1 minus 2 times mu of E2, right? And then the last term is m plus 1 times mu E m plus 1 minus m E sub m, and then mu of E m plus 1, right? Okay, so what is the middle term? Since each E sub 0 minus E1 and E1 minus E2, they are all disjoint, and then you sum them up, and then this actually in the middle term, it become from the first term minus the last term E of m plus 1 f integral over here, right? And then the right hand side, you can see the mu of E sub 0 is just the mu of x. And then plus, so each mu's of E1 cancel one term, and then they cancel second term, but all the way to this, it will become the sum of n from 0 to m mu of E n, and then remain the last term, which is m minus 1 and mu of E m m plus 1. And then here the same thing, right? So eventually it become the sum of n from 1 to m mu of E n, and then minus the last term m mu of E m plus 1, right? So this is the partial sum. Now let's see, so we want to prove like basically we want to prove the first only if part, right? So if f is integrable, then this sum of the infinity series converges. So basically we want to bound it. So from this part, you can see when n sum from 1 to m mu of En is less or equal than m times mu of Em plus 1 plus E0 minus Em plus 1 f d mu, right? So we want to prove this part, the only if part. So here, if you see, we can write this to be m plus 1 and then mu of Em plus 1 minus mu of Em plus 1 plus this E0 f d mu, right? So the reason we're doing this is because you see this one is actually you can write down this is the integral form. It's m plus 1 m plus 1 d mu, right? A constant integral over this, and then you plus E0 minus m plus 1 f d mu, and then minus this term. And here is actually less or equivalent because over E is m plus 1 set. F is greater than m plus 1. So m plus 1 is less than or equal to F. So if we write down this to F, we make it bigger. So this becomes, and then this two sets combined is E sub 0, right? F d mu minus mu plus 1. It's definitely this one is bounded by F mu, right? F is positive and non-negative, right? So we prove the only if part because this, when this is integral, this is a finite number. So the partial sum is finite, which means this converges, right? So the if part, so if you look at here, the if part, we have this inequality. If you look at here, now we have E minus m plus 1 f d mu is bounded by mu of x plus the sum from n from 0 to m mu of E n. Right? And then minus the term, right? So we can, so definitely this is bounded by this because it's less than this, bound by the less than this minus a positive one. So it's bounded by this. And then it is, okay, so this is definitely finite, right? Because the E part is like we assume this, this is this series converges. So this one converges, and then this is finite. So this is finite, right? But the left hand side, you can see this E m plus 1. The sequence is increasing to E sub 0, which is x, right? As m goes to infinity. So this one is actually, if we take a limit, it's the limit when m goes to infinity, this integral. And then it is increasingly, and which each, so the limit is finite, right? So that's it.